So welcome to another seminar today with also a recent doctor by our institute, Fernando Díaz-Díaz. So he's now in Carlos III in Madrid, no? With the group of in the GISC group.
Sí, with Ancho Sánchez.
With Ancho and so on. And so I think you've told us a little bit about side networks before, but I'm curious to see this expansion that you do of the graphs. So the floor is yours.
Thank you. Thank you very much. So yeah, I'm very happy to be here because, well, many things that I will discuss here I did during my last months at the IFISC here after I finished the thesis. Then I will also talk today about some things that I did during my research stay, which was part of my PhD, and I never told you about that part. And yeah, and well, now these things were finished on my new position, but they are actually from my previous time. So I think it's nice to share them with you. So, unsurprisingly, I will talk about sign networks, which is my topic, or as we say in Spain, yo he venido aquí a hablar de mi libro. And this time is quite literal because we have published a review, which will be a book. So I will talk about a libro, actually. But yeah, so if you have heard me some points, you know that I work on sign networks, which are networks with positive and negative edges, and they are the way of representing conflict or antagonism within complex systems. And this is very useful for practical purposes. We have this type of antagonism in biology, for example, inhibition in the brain or in gene regulatory interactions. In social systems, we have hostilities and conflicts a lot of times. Obviously, in international relations, war is a major player. In ecology, we have predation, we have parasitism, we have competition, and even in more abstract systems, we can talk about antagonism between, for example, time series, and this typically represents something of the actual real physical entities being studied. For example, we can have competition between companies in economics. And in all of these systems, negative edges play a major role. So let me give you a short overview. There are many works that have found, for example, that predator-prey interactions, which have a negative component, of course, especially negative for the prey, are very important for a stability criterion. It turns out that without this type of interactions, the ecosystems would not be stable. In gene regulatory networks, several researchers have found that negative interactions are important to let the system be robust against internal perturbations, but at the same time very flexible to external inputs. So you have something that can maintain homeostasis, but at the same time adapt to the environment, which is what typically living systems want to do. In economic and financial systems, it has been found that a property called structural balance, that we will talk a lot about, is correlated with increased performance in mutual funds. So if you want to make money, you should try to be balanced. In social systems, there is, for example, this paper that has found that knowing the structure of positive and negative connection between children can let you predict with very high accuracy whether two children will be friends or enemies. So one can actually kind of predict using network theorems the evolution of the relations between teenagers up to a given point. In the brain, I find very interesting that negative interactions and anticorrelations play a key role in creating different functional networks that let the brain do different tasks. And in particular, it has been found that these negative correlations are always present in the state of consciousness, but not when the people are unconscious. So it seems that it's very important to keep people conscious. And well, in wars, in international systems, I think you probably learned in high school that many international systems and many countries are profoundly shaped by their conflicts with other countries. Or if you see the news, you will also see that a lot. So I will not develop on that. Okay, so what are we going to talk about? Well, I've decided to mainly talk about three main topics. The first one is something borrowed from my thesis. It's an introduction about structural balance, which is arguably the most important property in sign networks, and other metrics that can be used. Then I prepared some slides about work that it's not mine, but it's on the field, and I think it might be appealing to many of you because it relates on how to define dynamical processes on sign networks. And then I will show you what I did in the research state, which was, this is a bit more mathematical, and basically consists of mapping a signed network to an unsigned one without losing information, and how we can use this to detect communities and factions in signed networks. Okay, so that's the plan. Let's start with the review, especially for the people that maybe are newcomers, about what is this structural balance thing. First, let me define what is a signed network. Mathematically, a signed network is a collection of three objects: a set of nodes, a set of edges, and a function that assigns an edge to assigned to its edge. This definition is quite mathematical and combinatorial, so typically we just represent the signed network as an adjacency matrix, and we put a +1 sign if the corresponding nodes are connected through a positive edge. So for example, 2, 4 is this one, and it's +1. And when they are connected through a negative edge, we put a -1. Having this represented as an adjacency matrix is very powerful because it allows to use the tools of linear algebra to study the structure. In particular, it's very useful to understand walks. Recall that a walk is a sequence of edges that can have repetitions, but that has the constraint that consecutive edges must be incident to the same node. So for example, if I do 1, 2, 1, 2, 1, that's a possible walk. The length of the walk is the number of edges, and the sign of the walk is the product, not the sum, of the signs of the edges. This is capturing the idea that we intuitively have that the enemy of the enemy is my friend, which is minus times minus is plus. So two negative edges form a positive walk. And this lemma, which is a very powerful tool, tells us that the case power of the adjacency matrix counts the difference between the number of positive walks of length k between two nodes and the number of negative nodes, the number of negative walks of length k between the same two nodes. So for example, if we want to know the number of negative or the difference of walks between nodes 1 and 3, we would just take, for example, for length 3, the cube of the adjacency matrix and look at the entry 1, 3, which here is -5. This is because there are 5 negative walks between these two nodes of length 3, which are 1, 2, 1, 3, 1, 4, 1, 3, 1, 3, 1, 3, 1, 2, 4, 3, and 1, 3, 4, 3. And I hope you are seeing that enumerating them is very messy and very annoying, and it's very easy to skip one, whereas computing this power is super trivial. So basically, this lemma allows us to convert a difficult combinatoric problem into a nice algebraic problem. Okay, this notion of the sign of a walk or of a cycle can be exploited to develop a theory, which is the theory of structural balance that was developed by Harari. And this mathematician said that a cycle is balanced if it is positive, if it only contains an even number of negative edges. So the enemy of the enemy is my friend is a positive and thus balanced cycle, but the friend of my friend is my enemy would be unbalanced. But we can extend this beyond triangles to squares, pentagons. And a network is balanced if every cycle within the network is balanced, and if not, it is unbalanced. For example, here, no matter how hard you try, you can see that you will never find a cycle with an odd number of negative edges because it's balanced. However, here, this graph is unbalanced because we have one cycle with one negative edge and one is odd. Balance has a lot of important properties that can be exploited and that are known as balance theorems. And the most important one, this one will actually play a big role in the last part of the talk, is Harari's theorem that tells us that when a graph is balanced, its node set can be split into two groups, which we call the balanced factions, such that all positive edges are within the groups and all negative edges are between the groups. So basically, when a graph is balanced, it has an objective way of being divided into two antagonistic groups. Whereas when the graph is unbalanced, it can be proven mathematically that this is impossible. No matter how hard one tries, one would always find, in physical terms, a frustrated edge. So either a positive edge between the two groups or a negative edge within the groups. So here you can see that balance has a very strong structural implication. Another theorem that it's interesting from the spectral point of view is that when a graph is balanced, the adjacency matrix and its entry-wise absolute value have the same spectrum. And if you think about this, it's quite powerful because having one matrix with signs and one matrix without signs that have the same eigenvalues is a quite remarkable property that is only achieved when the graph is balanced. Something that is also interesting, although it will not play a role in this talk, is that there is a notion of weak balance that generalizes the notion of strong balance. This was introduced by Davis, and a network is weakly balanced when it contains no cycle with exactly one negative edge. So this network is unbalanced because it has a cycle with 3 negative edges, but since 3 is not 1, it is considered weakly balanced. And we have an analog of Harari's theorem, which says that a weakly balanced network can be split into k balanced factions such that positive edges are within factions and negative edges are between factions. So the difference is that now, instead of 2, we have a number k larger than 2. So this is very useful for machine learning people because typically you expect to find more than one group in your data, more than 2 groups in your data. Okay, just a final reminder of what I did in the thesis. A very relevant question in this area is that to measure the distance of a network from a perfectly balanced state. And by this, I mean how close we could how hard we would have to work to find a perfectly balanced network. So for example, here we have only one negative cycle here, and therefore it would be relatively easy to go back to the balanced state. Whereas here we have many unbalanced cycles, so it would be hard. So intuitively we would say that this is more balanced than this. And there are 4 main approaches in the literature. The first one is just to count motif, to count the number of positive and negative triangles or squares and use them as proxies for the global property that is balanced. Then we have the frustration-based approach, which is basically to take the tools from spin glasses and physics and to import them. Again, we will talk a bit about frustration in the last part of the talk. The dynamics-based approach that will be important in the part about dynamics, which basically uses a dynamical process that depends on balance to be able to retroactively infer the balance. And the walk-based approach, which is to use the walk lemma to count the number of positive and negative walks and use those as proxies for cycles. And as you may know, this was the main approach that we used during my PhD thesis, and I have told here at IFISC a lot of times about these things, but today we will not talk about these things. Today, instead, we will talk about dynamical processing in sign networks, and just to give you a bit of context, let's first discuss the most simple dynamical process in an unsigned network. So probably if you wanted to model a very simple process that evolves in time, what you would do is to take, for a given node, all possible fluxes that go outwards, which are here the red arrows, and all possible fluxes that go inwards, that are the pink arrows. And probably, sorry. And probably you would also assign the rate of change as something proportional to the concentration on the node. If a node has a high concentration, it is more likely to spread that outwards. So you would probably write something like this. The concentration at t+1 is the concentration at node I at t minus the outward fluxes that depend on the concentration of that node and decrease the concentration, and the inward fluxes that depend on the concentration on the neighbors of the node. This can be written in a matrix form if you take the continuum limit, as the rate of change is proportional to this matrix, K minus A times the concentration. And this matrix, K is the degree matrix and A is the adjacency matrix, and the difference is called the Laplacian matrix because this is the discrete analog of the Laplacian operator in a continuum system. So this is the diffusion equation, the time derivative equal to the Laplacian, but for a graph instead of for a continuum system. The key operator for the diffusion equation is, of course, the Laplacian, which we have said that it's the degree in the diagonal entries, and it's the negative of the adjacency matrix in the off-diagonal matrix elements. And this is for an unsigned network. So the question is, how can we generalize this to a signed network? And it turns out that it's very simple. Let's see if you see the difference. It's here, the difference. You only add an absolute value here. So you take the degree irrespective of the sign of the edges. It only matters the number of edges, not the signs. However, the sign is included in the Laplacian through the part in the adjacency matrix. So this element can be positive if the element in the adjacency matrix is negative and the signs cancel out. This Laplacian, that I will call the signed Laplacian, has remarkable properties because, in particular, it is positive semi-definite. All its eigenvalues are larger or equal to 0, and it has the 0 eigenvalue if and only if the network is structurally balanced. So this is already suggesting that the structural balance of the network will play a key role in the dynamics that take place on them through the spectral properties of the Laplacian operator. Now let's do that in more detail. So we have this equation. I'm going to assume you all know how to solve this. It's the exponential. The only problem is that this is the exponential of a matrix, the Laplacian times the time. So we do an eigenmode expansion. Psi are the eigenvectors and lambda are the eigenvalues, and we have this sum over eigenmodes. But this exponential at long times will decrease towards 0 unless we have one eigenvalue that is equal to 0. In that case, the exponential is simply 1, and we have a non-zero concentration in the long time limit. So when the smallest eigenvalue is larger than 0, that, remember, was when the network was unbalanced, the stationary state is trivial and empty, null. Whereas when it's balanced, we have an stationary state that corresponds to the eigenvector associated to that null eigenvalue. That in a signed network will typically have +1 or -1. And very interestingly, do you remember that in a balanced network there were two balanced functions that were objective and came from Harari's theorem? Well, this eigenvector is +1 for one of the functions and -1 for the other. So this eigenvector reveals the functions. So what we have seen is that in a signed network, the diffusion can have 3 possible stationary states. In the trivial case of a signed network with no negative edges, so a signed network is a type of, an unsigned network is a type of signed network, a very boring type, but a type, you have consensus. All the nodes converge towards the same state. When you have a signed but balanced network, you have dissensus. One faction goes to one state and the other faction acquires the opposite state. So already linear dynamics are creating polarization. And when the network is unbalanced, you have absence of opinions. All the networks go towards 0. So you are getting kind of contradictions, and in the end, you don't polarize, you stay neutral. Okay, so this is already an interesting result for the most simple dynamics, which are diffusive dynamics, but I also wanted to tell you about some more complicated dynamics. And, well, before, this is one example of this very important result in network science that happens time and time again, which is that the structure of the network, in this case the structural balance, determines the nature of the dynamical process taking place in the network, and vice versa, the dynamical process can reveal the structural properties of the network. For example, if you run a consensus dynamics, so a linear dynamics, and you find this, you can know that the network is balanced. And if you find that it goes towards the stationary state very fast, it is very unbalanced. So this, especially the eigenvalues of the Laplacian, tell you through the dynamics the structural balance of the network. This is the dynamics-based approach that I mentioned before. Yeah.
How diffusion happens on a negative edge?
So if you come here, since this Laplacian only takes is positive, but the adjacency matrix can be negative, basically what it's being done is that nodes connected through a negative edge are trying to converge towards the opposite state of the original node.
Changes the damage.
It changes, yeah, it changes kind of the polarity, yes. If you want to see it in an intuitive way, it's like if you have a hot topic and your political adversary has opinion A, so you have opinion B. So if your political adversary likes bike lanes, you don't like the bike lanes just because the other one likes them, not because of any reasonable or argumented topic. You are just copying the opposite of the neighbor. Okay. So yeah, I wanted to tell you also a bit about other types of dynamics on signed networks. And well, we are in IFISC, so I was, of course, going to do the signed voter model, which has been defined, of course, by these guys. And okay, yeah.
So you raised your hand. Maybe you want to say something.
Okay. So yeah, the signed voter model. Basically,
Sorry. Can you hear me now?
Yep.
Okay, sorry. No, I just was trying to clarify about the previous question. And the problem is that the signed Laplacian, what is called the signed Laplacian, is not really a diffusive kind of Laplacian in the physical and mathematical sense of what we understand by diffusive, which is just the product of divergence times the gradient. So in reality, this Laplacian, well, we can call Laplacian, we can call Kentucky Fried Chicken, but it represents the superposition of two kind of diffusive processes of opposite sign. So one promoting the alignment between the positive links and the other promoting anti-alignment across negative ones. So it is therefore not a purely diffusive operator, but the generator of a competition between cooperative and antagonistic diffusion. There is a lot of confusion in the literature calling Laplacians to many things that really are not Laplacians in the diffusive kind of sense of that. And this is one example of them.
Thank you, Ernesto.
Thank you, Ernesto. Only one minor comment. This Laplacian can be written as the product of an incidence operator times its transpose. So it can be seen as a gradient, a divergence times a gradient. It's just that the gradient.
It can be expressed as a product that I have proved this in a recent paper, which is accepted now in special matrices. Yes, it can be written as the product of gradient operator, but it's not, well, incidence operator, but the first incidence is a kind of twisted gradient. It's not a proper, how to say, well, the twisted gradient is not a proper divergence operator. And it's a little bit technical, but really, although you can express as the transpose or conjugate transpose of an incidence matrix times the incidence matrix, the first incidence matrix doesn't represent a proper divergence. So this Laplacian is not expressible as divergence of the gradient with a proper gradient, satisfying that the gradient of a vector of ones is equal to 0. And this is not satisfied here.
Yeah, of course. Yeah, that property is lost. Yes, that's a very important observation. And in the Laplacian also, the Laplacian of the constant vector, it's not 0.
Yep.
Yeah.
Oh.
Thank you, Ernesto. Okay, so in this Vauter model, basically, what we do is for a positive edge, nodes copy the state of their neighbors. So the typical Vauter model, this blue guy copies the state of his friend and therefore becomes white. But in the negative edges, nodes copy the state of the neighbors, but swap it. So this guy is white, but his enemy is blue, and therefore, sorry, the other way. This one is white, but its neighbor is white, so it becomes blue just to be antagonic to the neighbor. This can be formally mapped to a signed random walk, in particular, the probability of a node I in being in the, let's say, the white state, here the state +1, can be written as this complicated equation, but one can recognize between all the clutter that it's a random walk, because a random walk has the inverse of the Laplacian times the adjacency matrix, which here it's split in the positive and negative parts, but one can arrange it, and therefore you can use for this the theory of signed random walks, or of random walks in general. And this in particular has the consequence that the Vauter model also has very distinct stationary states. One can have either a polarization, so one balanced function becomes acquires the state +1, and the other acquires the state -1. This happens, of course, if the graph is balanced. In unbalanced graph, the probability of the node being in the state +1 or -1 is 1/2, so you cannot predict the long-term dynamics. And therefore the average polarization of the system would go towards 0. Well, of course, if the network is unsigned, you will reach consensus, so you will find this polarization, but one of the functions would be empty. And curiously, because we have dynamics that are not time dynamics that are discrete, we evolved in discrete time steps, a new dynamical regime emerges, which is called which happens only in anti-balanced graphs, which are the ones that have positive connections between factions and negative connections within factions. And in this case, in one time step, the system is polarized, so these guys are green and these guys are pink, but in the next time step, they flip completely their opinions. All of these become pink and all of these become green. In the next time step, they go back to here. So we have a oscillation between the two opinions. So there is a polarization, but they are constantly changing signs within that polarization. This, of course, is we are doing deterministic dynamics. So we are neglecting all the stochastic effects that can have many important consequences, such ordering the system in for some dimensionalities, etc. So I think here there's a lot of work of doing to be done to consider the role of fluctuations, and also one can, of course, add many additional mechanisms. And as far as I know, very few things have been done in that regard, with one exception, that is the coevolving signed Vauter model, which was done by a guy named Maxi San Miguel and another guy named Raúl Toral, which you may know. So yeah, of course, I couldn't resist talking about this. What we did, well, not me, sorry. What they did is they basically considered that there are configurations that they called satisfying and configurations that they call unsatisfying. The satisfying ones are either, are these ones here, either friends in the same state or enemies in different states. And the unsatisfying ones are, well, enemies in the same state or friends in different states. What happens is in their model is that the unsatisfied configurations move towards one of the satisfied ones through one of three mechanisms. The first one is simply the voter model mechanism. So for example, here, blue and white, since they are friends, the blue copies the state of the white and becomes white, comes here. Another mechanism is swapping the sign of the edge. So these two are enemies, but then they discover that they share a lot of political thoughts, and then they become friends. And the third mechanism is rewiring. So this configuration can rewire by breaking the unsatisfying link and mapping to a satisfying one. The rewiring happens with probability R, which is the parameter that controls this, and the sign flip mechanisms happen with probability P. The other important parameter, by the way, will be the average degree of the network, which is mu. And what they found is that there are different regimes separated by phase transitions, etc. And the three regimes can be either a consensus where all nodes have the same state and they are all connected through positive links. What they call a two-group phase, in which there are two groups with opposite opinions connected only through positive edges within and negative edges between, and you probably have heard this before. And finally, in this small region of the phase space, there is a fragmentation in which there are two opposite opinions that are disconnected. What I find very interesting is that this is what I've defined as a structurally balanced state. So this paper is actually explaining a possible mechanism and the relevant parameter regimes in which this mechanism can create spontaneously structurally balanced networks, and explains a possible reason why structurally balanced networks appear. However, they don't say the word structural balance nor sign network once in the paper. So this exemplifies very well, in my opinion, something that happens a lot in this field, in sign networks, which is that people use sign networks without knowing they are using sign networks. And they reach very relevant conclusions for the field without even knowing about that. And this happens a lot. Like this happens here, where from the voter model approach, one gets to structural balance. But this also happens, for example, in neuroscience, where they have a lot of results about inhibition, but they haven't framed it in the terms of negative interactions. In ecology, there have been also many studies that have not been connected to sign networks. In data science also. So there are many disjoint fields that have not talked to one another, but that have the same phenomena occurring, and the same tools can be useful for them. So that's also one of the reasons we wanted to write a review to try to help a bit with that, because it's very difficult to orient in the literature. Okay, so some references that I think were interesting if you wanted to start. And now I'm going to start talking about the second part, the thing I did in Oxford. So if you have some questions now about this part. Yes?
In your voter model, the x is a continuous variable, or so when you apply the rules, you make it like minus, and the opinion is binary, or it is like a continuous variable?
I think it's binary.
No, in your voter model, in the previous.
Here, the state is binary. What is continuous is the probability of being in that state.
Okay. So what you plot is the probability.
Well, this is not exactly a probability. This is the average over fractions of the state.
Okay.
But yeah. I want to emphasize that these are not my results. Like, I don't want to get credit for this. This is things that have been done in the literature, and I thought would be interesting for you. Both this and the one from Maxi and Raul. Now, what I will describe, it's my work in collaboration with Renaud Lambiot and Karel Deprient. So, as I said, the idea is to explore ways of mapping networks to unsigned networks and to detect mesoscale structures, which I recall you are patterns that are neither at the local level, at the level of nodes, nor at the global level of the whole network. So the typical example is a community of like-minded people or a core periphery structure, etc. So I would like to ask you if you think that which of these, or both or neither, have a mesoscale structure. Like, think a bit about it. And the answer is that both have it. The difference is that here the mesoscale structure is in the localization of the links and not on their sign. And here the mesoscale structure is created by the distribution of negative signs. So this is what traditionally people call communities, no? Densely connected subsets of nodes. But this one, it's what I call factions because it's types, groups of nodes that are consistent with structural balance mostly. So they are mostly connected through positive edges within and mostly connected through negative edges between. If you want to think about it from an academic point of view, communities are the departments, are how you are connected to the people, regardless of whether you like them or not. And factions are the internal divisions within department, are who you ally with and who you fight with in a departmental council. Okay, so since we have these two types of mesoscale structure and we would like to detect them. And to do so, we would need a cost function to be able to optimize over it. So for communities, the cost function that we will use is the size of the cut set. A cut set is basically the number of edges that fall between the two groups or subsets that we partition. So for example, here, this is one subset of the partition. This is the other subset of the partition. This is the only edge that falls in the middle. So this edge is the cut set. The size of the cut set in this case is 1. And in particular, networks where we can reduce a lot the size of the cut set are networks that have community structure. On the other hand, for factions, the cost function that we define is the frustration set. Remember frustration from several slides ago. A frustration set is the set of edges that have to be removed in order to make the network balanced. So for example, here, if we remove this edge that is positive, the network would be completely consistent with the structural balance. So this edge constitutes our frustration set. And since the frustration set is small, the network has a faction structure. Okay, that about communities versus factions. Now we talk about the expansion. The idea here is to map, as I said, an assigned network into an unsigned network without losing information. And to do so, we first take the node set and copy it twice and assign a polarity to each node. So node V, now it's positive and negative. Then we take the positive edges and connect the nodes with the same polarity. So basically we duplicate them. And finally, for the negative edges, we map them to positive edges, but that map nodes with opposite polarity. So this edge UV gets mapped to U plus V minus and V plus U minus. Keep in mind that this expansion always duplicates stuff, and that now the information of the signs of the edges is encoded in the relative polarity of the nodes that are being connected. This expansion, if we want to use it, it has to fulfill a number of basic properties. And the first one that we proved it had is that it preserves a structural balance, but in a very particular way. A connected sign graph is balanced if and only if its expansion is disconnected. So this graph that is balanced gets mapped to two disconnected squares, whereas this graph that is unbalanced gets mapped to a connected octagon. So the Gremman expansion is expressing balance through connectivity. Now, we also have now a bigger space with attributes in the nodes, so we can define new operations and try stuff with them. One that is particularly useful is the involution. Recall that an involution is a function that it's its own inverse. So for example, -1 is an involution because you apply -1 twice and you do nothing. Or a reflection is an involution because the reflection of a reflection is doing nothing. So that's the idea. You apply it twice and you get again to the origin, to the same state. Here, the involution is swapping the positive polarities with the negative polarities. So for example, here, the involution swaps the gray nodes and the white nodes. Now, as we like to do in physics, this operation induces a symmetry that we can study and see if the symmetry reveals something. In this case, it's what I call the Greenband symmetry. And basically, a set is Greenband symmetric if it's invariant under the involution. So edge E1 is not Greenband symmetric because it gets mapped to here, not to itself. But the set E1, E2, the pair, is symmetric because even though the edges are swapped, the pair remains invariant. In particularly, we will be interested in the Greenband symmetry of partitions of nodes subsets. And partitions can be Greenband symmetric in two ways. Either each subset of the partition gets mapped to itself, which I will call Greenband symmetric, or another alternative is that the subsets of the partition are swapped. So each subset changes, but the partition does not, because we have just swapped the two. And I will call that Greenband antisymmetric. Finally, just as a remark, one can also define an operation that projects the expanded network back to the original one. So that's the operator we will use if we want to recover information in terms of the original sign graph. And it amounts to just removing the polarities of the nodes. And then you have a projection. Okay, so far, what we have done is we have defined two types of mesoscale structures, communities and factions, and two types of cost functions associated to each, the size of the cut set and the size of the frustration set. And in parallel, we have defined a map from a signed network to an unsigned network. We have seen that in the bigger unsigned space, there is a new notion of symmetry that is related to this involution operator. And also we have a way of projecting back. And now the question is, what types of structures in the expanded space are representing communities and factions from the original space? If we knew this, we could use community detection in the expanded space to detect things in the original space. And it turns out that there is a bijective map from cut sets to cut sets and frustration sets. So when you have a cut set in the signed network, this maps to a Greenband symmetric cut set in the expanded network. And when you have a frustration set, it also maps to a cut set in the expanded network, and vice versa. Any Greenband symmetric cut set in the expanded network will correspond to either a cut set or a frustration set in the original network, and we can determine which one it is by looking at the symmetry. The Greenband symmetric partitions induced by the cut set will correspond to cut sets in the original one, and the antisymmetric will correspond to frustration sets. And since this is a lot, let's see some examples. Here we have a Greenband expansion, and we look at this cut set. It's clearly a cut set because if we remove it, we disconnect the network. And this cut set induces a partition, and the partition is Greenband symmetric because if we apply the involution, which in this case would be reflecting along this horizontal line, this node would get mapped to this node would get mapped to this node, but the blue subset would not change and the orange one would not change either. So this is Greenband symmetric. The theorem tells us that this maps to a cut set in the original graph. And indeed, these two edges map to this edge that was the cut set in the example we saw before. Now, this more complicated Greenband expansion also has a cut set, which are these two nodes. But now the partition induced by it is Greenband antisymmetric. This node goes to this node. So the involution maps the orange subset into the blue subset and the blue subset into the orange subset. The theorem tells us that then this cut set will correspond to a frustration set in the original graph, and indeed this edge here was the edge that we had to remove to make the graph completely balanced. So it's a frustration set. Okay, so that gives us already the main result. We now have a way to understand mesoscale structures in an unsigned space. Now, what we do is we apply the standard tools of community detection in the unsigned space and then trace them back to the original space to get information about the signed network without having to develop tools for signed networks. I will use spectral clustering mainly for two reasons. The first is that I like eigenvectors, and the second one, and perhaps less subjective, is that it has nice symmetry properties that are particularly well behaved when combined with the Greenbank expansion. As a quick reminder, spectral clustering basically takes a graph, computes its Laplacian, and uses the eigenvectors of the Laplacian to do an embedding into a low-dimensional Euclidean space. This step is called spectral embedding. And then, in this low-dimensional space, one applies k-means and finds clusters that correspond to the communities. So we need a Laplacian. We already saw what a Laplacian is. So we start with the adjacency matrix, and in this case, we will split it in the submatrix containing the positive edges and the submatrix containing the negative edges. One can show then that the Greenbank expansion has an adjacency matrix of this form, A plus, A minus, A minus, A plus. And then we compute the Laplacian in the expanded space, and it would look something like this. And this expanded Laplacian has a very powerful property, which is that can be block diagonalized. And the blocks of this block diagonalization are not random matrices, but are precisely the Laplacian of the unsigned network and the Laplacian of the signed network. So this is telling us that the Greenbank expansion is simultaneously containing the information of the signed network and its unsigned backbone. Moreover, the eigenvector, if a vector is an eigenvector of the signed Laplacian, then this eigenvector leads to an antisymmetric eigenvector in the Greenbank expanded Laplacian. And if for eigenvectors of the unsigned Laplacian, those get mapped to symmetric eigenvectors of the Greenbank Laplacian. So there is a parallelism here, because we said that communities are related to the unsigned topology, that it's encoded by the unsigned Laplacian, and this unsigned Laplacian get mapped to symmetric eigenvectors. And at the same time, before we said that communities have Greenbank symmetric partitions. And on the other hand, factions depend on the distribution of edges, which is encoded in the signed Laplacian, which has antisymmetric eigenvectors, and at the same time, factions have antisymmetric partitions. So now we can use this to determine this. And that's the idea. So the algorithm now the math part is over. Now this is the recipe, and I guarantee you that it works. You have theorems that say that this works. You just take the graph, expand it, compute the Laplacian, diagonalize it. Each of these is a line in Python. Now you use the eigenvectors to do an embedding, you run k-means, and then the clusters, you see their symmetry. If they are symmetric, they correspond to communities in the original one. If they are factions, they correspond, if they are antisymmetric, they correspond to factions in the original signed network. So this algorithm is able to detect simultaneously communities and factions. Before, typically, you had either an algorithm that detected communities or an algorithm that detected factions, but not both at the same time. And it is able to disentangle them if they are simultaneously present. To show you how this can recover both, we have these graphs in which we tested 3 possible community detection methods, with the unsigned Laplacian, with the signed Laplacian, and with the Greenbank Laplacian. And we created stochastic block models with a ground truth partition that was interpolated between pure factions to pure communities. And we evaluated the overlap between the ground truth and the detected partitions through the algorithms. As you see, the unsigned Laplacian is terrible in this region, the signed Laplacian is terrible in this region, and the Greenbank Laplacian is consistently good, except in this area, which we can talk about in the question session if you want. And let me give you a second example, which is a network that has, yeah. The adjusted run index is basically an overlap of it's the number of pairs of nodes that are consistent between the ground truth partition and the partition detected by the algorithm. And the other one is the normalized mutual information between the ground truth partition and the detected. So they are measures of quality. 1 means good, 0 means bad.
All that if what's explained to us is deterministic, that you obtain for a Riemann expansion a value different from 1.
Yeah, that's the value. Okay, we can talk about this now. Basically, this amounts to the question of what should an algorithm return to you if the network has no structure? Here we have communities, here we have factions, here we have nothing. So you're asking the algorithm to recover the structure without having any. So it has to get labels, but the labels are essentially random because there is no mesoscale structure here. So actually, the surprising thing is that it's not 0, because there is very, very little structure here. We neither have positive edges within, negative between, nor differences in the connectivity. And actually, that's why this plot is here. You see that precisely when the value drops, the eigenvalues, the spectral gap between the two Laplacians becomes 0, which indicates that there is no dominant structure. So this confirms that this drop is because there is no dominant structure in this parameter regime. Okay, thank you. So another example. Here we have a network that has both communities and factions. The communities are the hexagons, and the factions are these triangles that you see that within each hexagon there is 2 antagonistic blocks, this and this, and this and this. So if we do the algorithm that I explained, we first do the Riemann expansion, then we compute the Laplacian, then we compute the eigenvectors, which are these, and when we use the components of the eigenvectors to embed the nodes in a 2-dimensional space. In this case, we get 4 clusters that k-means would clearly recover. And for example, let's look at this one. This corresponds to 1 plus, 2 plus, 3 plus, 4 minus, 5 minus, 6 minus. This is telling us that we have a faction because it's antisymmetric, and the 2 factions in this cluster are, on the one hand, 1, 2, and 3, this triangle, and 4, 5, 6, this triangle. And if we would do this, the same analysis for this cluster, we would recover the other factions. Now, to get the communities, what we do is we need to obtain symmetric clusters. And in principle, it seems that there are no symmetric clusters, but actually, if you join 2 antisymmetric clusters that are involutes of one another, you get a symmetric cluster. So here you would get 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, 6 plus, and also all the minus ones. And this would correspond to the whole hexagon. So if you merge the 2 factions, you get the community. The factions live within the community. And if you think about it, it's impossible to have faction structure if you don't have a community structure before. If you don't have many edges, you cannot have many negative edges in between. So this is a way of separating the 2 structures. So the take-home messages would be, first, that we have 2 mesoscale structures in signed graphs, communities and factions, and they should not be confused with one another. I think that's already sufficient important message. Second, that there is this operation, the Riemann expansion, that separates that maps a signed graph into an unsigned graph without losing properties, and that this can be used to detect communities and factions in a principal way and separate them. And the separation is related to this notion of symmetry in the expanded space. And yeah, that's everything. Thank you very much. Yeah, and you can.
There are questions in the audience?
Thank you very much. Excellent. Two quick questions. Can I apply this to a network that only has negative ties?
Yep.
Okay. And this notion of community and fraction, mathematically clear and beautiful, how does it land with, let's say, political scientists or social scientists? Does that intuitively make sense?
Yep, actually there are, I can send you a work if you want, but they argue that communities correspond to what they call weak echo chambers and weak polarization in social systems, and factions correspond to a strong polarization. So one type of polarization is you do not make contact with the people that are in the other group. And the other type, which is the one that, for example, is very typical on Twitter, is you do make contact, but that contact is extremely hostile. So you interact to insult them and say they are wrong. And they are distinct notions of polarization, one that corresponds to community, another corresponds to factions.
Hi, very interesting. I have essentially two questions. One, here everything is motivated by diffusion, right? The underlying dynamics is diffusion. But think about, for example, the brain. So this is excitation, right?
Mm-hmm.
So there is not equivalent to diffuse to the negative value, right? So it's basically if you fight or not. But negative fighting is a concept that is, at least is not obvious to me, right? So in that case, I don't see why this assumption will tell us something about the inhibition in the interactions between networks, because I mean, there is no symmetry between 0 and 1, or minus 1 and 1. Here is asymmetry, right? To fight or not to fight.
Yep.
And the second thing is also in analysis of function and fMRI, for example, in the brain. There you can have correlations, right? When you calculate correlation can be positive and negative. But on the other hand, distances are not positive and negative, right? So you can transform from correlations to mathematical distance. And there you have a value between 0 and 1, right? And this is mathematically exact.
Mm-hmm.
So my point is, if you calculate communities with the distance based on the correlations, and then you calculate the factions of the correlation sign network, there is a connection between this thing or not?
Yeah.
That's
okay. Thank you. I have thought a lot about this actually, because from a personal point of view, this operation that is typically done when working with correlation matrices, which is typically use, I think it's the square root of 2 times 1 minus the correlation to define a distance. It is true that this is a well-defined distance, but the problem I see is that if you do this for a network instead of for a correlation matrix, what you are doing is mapping the negative edges to an absence of edge and mapping the absence of edge to a weaker positive edge. So I think that this transformation in some cases is distorting some of the properties of a network, I would say for sure. Of a correlation matrix, it's complicated. I don't know the answer. I would bet yes, but maybe not. And I would argue that when you have correlations in particular, you have this important property encoded in the signs. For example, that if 2 nodes are anticorrelated and one is anticorrelated with the third node, then the other one would be kind of correlated with the. So if you have one entity that is correlated with this entity, and this one is anticorrelated with a third entity, just by mathematical need, these two would be at least somewhat anticorrelated. You cannot have full correlation, full anticorrelation. So just from the mathematical structure of correlation networks, properties like structural balance appear naturally. So I think these types of things would be useful for correlation matrices and correlation networks, because they are, the fact that minus times minus is plus is already forcing the system to implicitly go towards balanced states and these things. With regards to the
But you don't know if, I mean, my question would be just mathematically, how the factions are translated when you consider the distance. Because now you only have communities. My question is, if the factions remain identified as communities, but you use the distance or not?
Okay, no, I don't know, but I would argue that the factions are actually the real clusters, because you would typically want groups of entities that are correlated with one another and anti-correlated with the rest. My question, which I don't know the answer, is how well this transformation preserves that, or if there are cases where I know that it has been used by many people, so in general it works well, but I am curious if there are cases where this might miss something that this approach would not miss. I haven't looked at it, but I have it as a possible idea to explore in the future. And regarding the neural dynamics, that's true. One of the key challenges of this is that mathematically it's clear what a minus sign is, but not everything that is hostile or inhibitory is precisely modeled by a negative edge. So one example is the neural dynamics. Another example, for example, is in social dynamics. It is not true always that hostility behaves as the opposite of friendship. There are cases where hostility and friendship have different dynamics associated, and one is not the negation of the other. In international relations, for example, an alliance is clearly not the opposite of a war, in the sense that war has stronger implications than alliances in terms of the life of the people living in the country. That's a big challenge, but my opinion is that it is good to have a common basis from which to approach the problem. And then, of course, for each individual problem, you have to decide which modeling choices are appropriate and which ones are not appropriate.
Any other questions in the room?
Thank you, Fer, for this cool talk. My question is about the Greenbaum spatial. Are you planning to use it to solve other problems of sign network besides community and faction detection? Because I'm sure you do, but I'm thinking about measures of centrality and net effect, because I don't know why.
Yeah.
And because if you transform a signed network to an unsigned network, but based on connectivity, I guess that measuring centralities in unconnected networks is also a problem itself. So it's not going to be useful to do this kind of expansion. Do you have any thoughts about?
Yeah, I that's the next step, actually.
Oh.
That's what I wanted to do next. And yeah, well, first, the network only disconnects if it's balanced, and having perfect balance is quite strange. And even if if it happens, you just treat it as a separate case. You check if it's balanced, and if it's balanced, you do something else. My main question is that you have two copies of the nodes in the expanded graph. So you have two centralities for each node. And I would like to know what those centralities mean. Maybe one is the centrality of the unsigned network, and the other is a purely signed centrality, or maybe not. Maybe there are two ways of thinking about centrality when the network is signed. I don't know. There are many questions there.
Cool.
Okay, so maybe I think Ernesto, do you have another question?
If I have time, yes.
Yeah, I mean, well, do your question and I'll stop it if it's too long, okay?
Okay, so I have 3 questions, so I will try to condensate them. But the most important one is that you are duplicating the size of the graph. So this has tremendous consequences for the numerical analysis of the processing. You are taking spectral values. Have you approached how the complexity of the problem increase now by this approach? This is the first part. Then related to this, you mentioned balance in one of the slides, But the main problem in balance is not to decide whether the network is balanced or not, but to quantify how balanced it is. So is this approach something that can give you a quantitative value of how balanced the network is? And the third part is, well, you obtain factions, as you call, but there are several methods for detecting factions. So if you focus only on the same work that you did in your thesis, what is the advantage of the new method for detecting factions in relation to the previous one?
Okay, thank you, Ernesto. So regarding the first question, yes, computationally this is far from ideal, but I would point out the fact that you duplicate, so the complexity class does not change. So if your community detection method is polynomial, then duplicating the size of the graph increases it. So instead of n, O of n to the k, you have O of 2n to the k. You don't get to a new complexity class. So,
yeah, but it's not the same 10 to the power 2 that 1000 to the power 2.
Yeah, and in this case, you would go from 1000 to the power of 2 to 2000 to the power of 2, which can be prohibitive in some context, and in other, it may not. So, for example, in our international relations network, this is perfectly applicable. But for large-scale social networks, there would be a problem, of course. Regarding the second question about the level of balance, this is the frustration-based approach. So you can measure the level of balance by computing the size of the minimum frustration set. That said,
which is an
exactly
complete problem.
I wouldn't do this way. I would measure the level of balance using the tools from the thesis, because they are much more manageable. So yeah, the Strada-Penzi balance index would be a much better choice for that particular problem. But the problem here was the detection of factions, not the measurement of the level of balance. I think for the level of balance, we already have the right tools. And finally, comparing this to the thesis, that's actually a fun question, because this graph, I tried to do it to use this graph for the thesis, and I had precisely the problem that I was explaining. Our method from the thesis detects factions, but it cannot detect communities.
No, of course. We did a method to detect factions, not to detect communities.
Yeah, so that, for example, for this graph, our method would get I'm not sure, but it may even fuse this one with this one, because negative times negative is positive, so the embedding would place these nodes very closely in the communicability space. So yeah, when it's a matter of context. If you want to detect factions and you want to take into account all possible walks, taking into account their signs, then use communicability. If you want to disentangle them, I think the Gremban expansion is a better choice. And one can, of course, combine them, in the sense that I started using the Laplacian in this slide, but until this slide, everything is independent of the methods used. So in the paper we published, actually, I think in the supplementary information, we proved that the communicability also has this property, also block diagonalizes, and it's the communicability of the signed network and of the unsigned network. So one could combine what we did with the communicability for signed networks and for unsigned networks here.
Great. So if the boss allowed me to make a comment about the previous question related to the brain, I do it, and otherwise I just...
Go on.
Okay, so I don't know who is the person, but basically what we have in the brain well, you can have diffusion in the brain. There is a lot of diffusion in the brain. In the examples that you mentioned, of course, there is directionality, and every time that you impose directionality or signs in the graph, you don't really have proper diffusion. So what you really have is a reaction diffusion process there. So there is a paper in PLOS Computational Biology 2011 by Barsny et al. They propose a method for reaction diffusion in which the reaction potential is just introducing signs into the network. It has several problems because the propagator of the model is not Markovian, and there are several problems that we have solved by making this operator self-adjoint. And but it's just that the methods that has developed Fernando are maybe well, the second part, yes, they are diffusive, but diffusion is not is a random walk, or it can go with the same probability in one direction or in the other direction. So then maybe it's more in the more general context of reaction diffusion.
Okay, thank you, Fer. Let's thank the speaker again. You'll be around still?
Yes, well, I live at